Okay, so hi everybody. Uh, Today, what I want to talk to you about is how we interpret this plot, which shows the redshift of a galaxy as a function of its distance away from us. And this is an important plot because it connects two very different parameters with different galaxies: the distance they are away and something about the properties of their light. And at first, these might not appear to be in any way related, but in fact they are. And this is called Hubble's law, but based off of the first astronomer who documented it well. And what I want to first talk about is how we understand this diagram and what it means. Now, there are a variety of different processes that can produce redshifts, changes in the wavelength of light. And one of the most natural ones, the ones we're most familiar with, are Doppler shifts, shifts in the wavelength of light due to the motion of the source. We do not think this is what causes Hubble's law, and I want to provide some evidence for that. And I want to then explain why these redshifts are instead interpreted as reflecting something involving general relativity. Now, the idea that these are Doppler shifts is not an unreasonable one. We can, in fact, look at this curve and interpret these as Doppler shifts. There's nothing intrinsically wrong with that idea. Changes in velocity do produce changes in the wavelength of light, and we can even convert these redshifts into what speeds those objects would have to be moving in to produce this. Now, because all of these galaxies have their wavelength shifted to longer wavelengths, that implies they're all moving away from us. And furthermore, that more distant galaxies are moving at higher speeds. And we can even make that quantitative by converting the redshifts into proper velocities. And we can see that we have very high velocities here of order thousands of kilometers per second. Now, at first, this might look like it's unlikely because it implies the Milky Way galaxy, the galaxy we are currently in, is a special galaxy, that basically all of the other galaxies are trying to get away with it from us, and those further away from us are moving away from us at higher speed. That seems to imply we're in some sort of special location relative to other galaxies which are moving away from us. This would violate the Copernican principle, the idea that we're not at a particularly special place. Since there are many galaxies similar to the Milky Way, why is this one special? However, in practice, this is not the issue. It's not that this trend implies that we specifically are special. If we instead consider the perspective of someone in, say, this galaxy here, which is moving relative to us, we can actually see they will have a very similar experience. So let's consider that. Let's consider this set of galaxies, which are evenly spaced in both speed and position, and consider the perspective of the galaxy right here. Now, from their perspective, they're not moving, just like from our perspective, we're not moving. But from their perspective, we are moving. Since in our frame, they're moving 2,000 kilometers per second to the right, in their reference frame, we will be moving 2,000 kilometers per second to the left, like so. But we can also consider other galaxies, like say this galaxy here. This galaxy is moving 4,000 kilometers per second to the right, whereas this one's only moving 2,000 kilometers per second to the right. This galaxy, from these guys' perspectives, is therefore still moving to the right because it's moving faster to the right than this one is, but it's not moving as quickly. In fact, it's just the difference between these two speeds, and you end up getting 2,000 kilometers per second this way. And all you basically do is have to either add or subtract the appropriate extra velocity vector. And what you will get is that this galaxy sees the same basic behavior as we do. And in fact, you can do this for any galaxy. Any one of these sees galaxies moving away from it and just the increasing speed with distance from that galaxy. So this trend does not imply the Milky Way is special. All it would imply, if these are in fact Doppler shifts, is that there is some place that is special. There is some place and all of the galaxies are moving away from that particular place with speeds that depend on how far they are from that place. So this is a problem because this picture of galaxies flying out into space is what a lot of us have in our heads when we hear the phrase the Big Bang. And that's actually somewhat sensible. That's kind of what the name evokes. But we don't think this is what happens, because even if we're not at a special place, it's still problematic to have a special place exist in the universe, because that would have all sorts of implications for what the distribution of galaxies, et cetera, would look like. For example, if galaxies were if there was a special place and all the galaxies were moving away from it, you would expect to be able to see trends across the universe. You might expect galaxies to be smaller as you get further from that special point. You might expect differences in the types of galaxies or their density. And even if we don't know exactly where we are, we would expect to be able to point to a trend that indicates that that special place is in one particular direction. And we don't see any evidence of that. If we look at surveys of galaxies, this is only over one part of the sky, but we have these over several parts. There's nothing really obvious about one side versus the other, which tells us that stuff started over here and moved over here, or vice versa. Everything looks pretty homogeneous on the larger scales, indicating there is no preferred location. And that's very hard to reconcile with these being Doppler shifts. So that is not the current interpretation. The current interpretation is much weirder than that and is involving, again, general relativity. Now, in general relativity, we know that there are other processes that can change the wavelength of light. For example, there are gravitational redshifts, which we've already talked about in the context of stars, black holes, etc. But what these reflect is the fact that gravity is not a force, it's a distortion in the geometry of both space and time. Now, the cases we've talked about have been involving how these distortions in space and time change basically the paths objects take when they're not acted upon by normal outside forces. But this doesn't just affect, say, paths, changing them from what look like they're straight to what look like they're curved. It also affects scale, the distances you measure. And so what this means is that if you have a bunch of objects which have mass and they're distributed throughout the universe, this is just showing a small patch of them, the collective gravity of that material can change the scale of the universe, which is a geometrical parameter, so that over time, the average distance between these massive objects changes so that they might be closer packed in the past than they are today. And this sounds at first like the same sort of idea, things are moving apart. But the thing is, they're really not moving. The space between them is changing because of how the geometry of the universe is changing. It's actually adding space between objects without those objects actually moving, which is fundamentally weird. And means that there is no special place in this system. The entire universe had its galaxies closer together in the past, not because they moved from one place to another, but because that just changed the geometry of the entire universe. This also has implications for how we understand these redshifts. if we imagine two galaxies and light comes from one and goes the other, in this case, the light wasn't emitted at a different wavelength because it was moving. As it flew between the galaxies and the distance between the galaxies got bigger and bigger, the distances between the crests of the electromagnetic wave get bigger and bigger, causing the wavelength. So these are no longer shifting because of motion, they're actually literally getting stretched as the geometry of the universe changes. This is what's called universal expansion or cosmological redshift in this particular context. Now, you might go, wait a minute, does this mean that, for example, the size of galaxies changes over time? Does the size of us, atoms, planets, do those change? And the answer to that is no, it does not. The thing to remember is general relativity says that the geometry changes associated with massive objects distort the trajectories they would take or how the motion works of objects when no other force is applied. When we're talking about atoms or planets, which are held together by chemistry, those are forces. Those are things that aren't just moving along free paths. So the size of a physical object, like a person or a planet, doesn't change due to universal expansion. You might think, well, wait a minute, what about solar systems or galaxies when you have objects in orbit around other objects? In those cases, the gravitational interactions amongst the objects themselves overwhelms the change in geometry that is causing universal expansion. So in practice, planets, stars, solar systems, even galaxies don't change in size as the universe expands. It's only these very separated objects whose distances change in response to this basic aspect of the geometry of the universe changing. It also affects the wavelength of light because pulling apart the crest of an electromagnetic wave doesn't do anything to it. There's no force resisting that pull, so it just happens. This also explains why we can get variations. For example, the Andromeda galaxy is actually gives a negative redshift. It's a blue shift. Now, that isn't saying that this violates this basic idea, because galaxies can move. They can have Doppler shifts. Andromeda is heading towards us at a fairly decent clip. The galaxies in clusters are all interacting with each other and moving relative to each other. These relative motions do produce shifts, but the shifts we're talking about correspond to speeds of about 1,500 kilometers per second or redshifts of about 0.005. This is enough to cause some scatter in the trend. Like, this galaxy is probably moving away from us physically. This one's probably moving towards us. But those are small corrections on top of this overall trend. As the redshifts get bigger and bigger, those motions just become a little bit of extra noise. And Andromeda is just close enough to us that that overwhelms the redshift due to cosmological effects, which would be very small. Now, the big thing about this insight is that it means we have to reinterpret what we're seeing here. The thing is, we're no longer seeing something that's intrinsic to the galaxy. Instead, we're seeing how the overall geometry of the universe has changed between when the light was emitted and when it was received. So this is now telling us something about history. So this is a different way to look at things. So, for example, we looked at this spectrum of a galaxy before. The wavelengths of features that would normally have occurred at 500 nanometers got moved to 600 nanometers. What that means in this case is the average distance between galaxies also increased by that factor. So when this light was emitted, the distances between galaxies, the distances between crests of electromagnetic waves that were propagating freely, was 5/6 of its current value. We parameterize this in terms of something called a scale factor. It's just a number that says how big things were in the past on the largest scale relative to how big they are today. So when this light was emitted, that scale factor is 5/6 its current value. And we usually make the current value 1. So in this case, we can say, okay, the typical redshift of galaxies, of light from galaxies that are 100 million light years away, is about 1%, or about 0.01. That implies that the universe scale, the average distance between galaxies, increased by about 1% between that time when that light was emitted and today. So we can say that the scale factor in this time in the past was 99%. So it's grown by 1%. And you can do that for any of these other points. So we can say that the scale factor of the universe was smaller in the past. This is why we call it cosmic expansion. The universe's scale, the average distance between galaxies, has increased over time. And because these more distant galaxies, light from them takes longer to get to us. Now, we can even look at more distant galaxies. We can go all the way to 300 million light years ago, and we can see the scale factor is more like 98%. And we can go even further than that. We have now measured the redshifts of galaxies up to 40 billion light years away. And at that point, the scale factor was almost half its present value. So we really are seeing these changes. Now, these changes are, again, reflecting changes with time. But now we have to be a little careful, because as the universe has expanded, the distance between these galaxies has changed a lot. And this light was emitted when the galaxies were closer together. So you have to take that into account when you convert this distance into a time. So, but you can do that math, or people who are clever can do that math, and make a plot like this, which shows what the scale factor is as a function of the amount of time the light would have taken to get to us. And you can see it's kind of a straight line. So over time, the universe has expanded. 10 billion years ago, the average distance between galaxies was about half of what it is today. And this obviously raises the question, how far down does this go? And this brings up a question, is this a real thing? And do we have other evidence for this sort of expansion? And we do, and it comes from a very different source. It comes from something called the cosmic microwave background. Fortunately, the cosmic microwave background has a very descriptive name. Each word in its name means something. In particular, it is a radiation in the form of microwaves, which are a type of electromagnetic radiation from the electromagnetic spectra with wavelengths between 1 millimeter and maybe 10 centimeters. People argue about the exact definition, but that's roughly where it is. If you take a telescope sensitive to those wavelengths and point it in the sky, you measure a signal. And it's almost the same signal from everywhere in the sky. This is why it's called a microwave background, because it seems to be coming from everywhere. If you could see the sky at these wavelengths, you would see something very uniform. There's some signal from the galaxy, but not very much. And in fact, we can see this signal is actually behind distant clusters of galaxies. So this is coming from everywhere. Now, the reason this background is important is because we think it's cosmological. That is, we think it is a relic from the early universe. And the reason for that is that it has to do with its spectrum. The spectrum of this microwave background has been measured very accurately. This is a plot showing the brightness as a function of wavelength. These crosses are data points, and those data points fit remarkably well a blackbody spectrum. And we've talked about this before. Blackbody is a theoretical predicted spectrum of an object that is a perfect absorber and emitter of light. And the shape of that spectrum depends only on temperature. This is the most perfect blackbody spectra in nature ever measured. It perfectly matches a spectrum for a blackbody at a theoretical temperature of about 2.7 Kelvin, just a few degrees above absolute zero. Trick is that doesn't make any sense, because at those low temperatures, things don't produce nice blackbody spectra. Blackbody spectra we can make decent approximations of, but only at high temperatures. Only at high temperatures do things act like they can absorb and emit all radiation well. The reason for that is at high temperatures, atoms tend to break apart and you deal with free charged particles. In metals, that happens at lower temperatures because the electrons are relatively free to move independently, and charged particles interact well with a lot of different wavelengths of light. But as you cool them off, those free charged particles reassemble into neutral atoms, and those only interact with certain wavelengths of light. And this is true. It's very hard to make blackbody spectra at low temperatures. So we have an apparent contradiction here. The spectrum is that of a perfect blackbody, but those shouldn't exist at lower temperatures. And the thing is, universal expansion explains this apparent paradox. The thing is, as the universe expands, the wavelength of light increases. But it doesn't just do that. It also pulls the various bits of light apart, reducing its density. So if you have light that is short wavelength and tightly packed, it gets spread out and its wavelength gets longer. This turns out to do something interesting. What it does is it takes a blackbody spectrum and turns it into a different perfect blackbody spectra, just at a different temperature. And in fact, the temperature is inversely proportional to the scale factor. So if the universe expands, the temperature of any blackbody radiation in it goes down, and it goes down by the scale factor. So let's think about that. What are the implications of that? In the past, the scale factor was smaller. That means the temperature was higher. So we have galaxies from when the scale factor was like half of its present value. Today, the CMB is 3 Kelvin. Back then the scale factor would be 6 Kelvin. And in fact, we have evidence for this because of how that CMB interacted with some of the gas around galaxies and galaxy clusters. We do know that have evidence that the temperature was somewhat higher at this time. But now let's push this even further back. What about when the scale factor was 0.1? We can guess it might have reached that. You get 30 Kelvin. What about 0.01? You might say 300 Kelvin. What if it got as low as 0.001? It would get up to 3000 Kelvin. We're now talking about the temperatures of plasmas, things that produce proper blackbody spectra. And this is how we interpret the CMB. Basically, in the past, things were not just packed closer together, they were also hotter. And what we're seeing here is remnants from that early phase of the universe's history when it was very hot. Just the wavelength of that light got stretched out to produce this particular black body on this particular time. So these are the two kind of key points that give us an idea about how our universe has evolved over time. The distances to galaxies from Hubble's law indicates the universe's scale has changed. Things were packed closer together in the past than they are today. The cosmic microwave background implies that not only was the universe more tightly packed, it was also hotter. And so this is why we think the universe started out in a very hot and very dense state, and it's been expanding and cooling ever since. This is what we really mean when we say the words Big Bang. It's that hot, dense state in the early universe. And what we've been endeavoring to do is understand that state and what has happened since then, which is what we will talk about on Friday. Thank you much for your time and attention.